Hi there everyone, it's Mr. Pope from Wilmington Grammar School for Boys, and today I'm going to be taking you through a crash course in series and expansions. I'm going to be talking about a little bit of sigma notation, even though I won't be looking at the whole host of sequences and series, for example, arithmetic, geometric, that kind of stuff. I had planned to be going over sequences and series, a closer look on the 29th of July on the fast track extension work on my Google Classroom. And when it comes to series, which by the way are just infinite sums, I just mainly wanted today just to get you used to the idea of taking something that is essentially infinite and being able to condense it down into, 1 or 2 centimeters worth of writing, which is always an incredibly powerful thing to be able to do. Now, what I'm going to be talking about today is I'm going to be looking at series, the binomial expansion, so a little bit of what we'd be considering Year 12 AS binomial expansion, and then moving on into the more general binomial expansion. Then I'm going to be looking at the Maclaurin series, and then in general the Taylor series today, and I think we'll stop at the Taylor series and using the Taylor series to estimate or give answers to differential equations at that point. The Maclaurin series you would be looking at if you were in your second year doing further maths for Core Pure 2 for that Excel course, and for Taylor series I believe it's further Pure 1, which you might not be sitting that module, but it's always interesting to know. Just in general, why are these sequences and series particularly useful? Well, whether you want to numerically approximate an integral, for example, or you want to solve a particular problem and you want a rough estimate. In mechanics, if there's a small angle approximation, we use the Maclaurin series for sine and cosine. That's what the small angle approximations are. Generally speaking, series expansions, whether they're Taylor, Maclaurin, or in more general, when we'd be looking at complex functions, the Laurent series, they're just useful because essentially, given an input, as long as you can add, multiply, subtract, divide, and perform all the other, well, all the arithmetic operators, really, then you can compute something. Whereas solving differential equations tends to be quite tricky, especially if they're non-linear. Ordinary differential equations are fine, but partials tend to get a little bit trickier. And in general, it depends on the form. There isn't one size fits all method with differential equations. But at least with series expansions, we can at least attempt to numerically approximate. So, right, what is a series? Let's suppose I have a number. Let's call it A0, the first number. Now we could put A1 as the first, but generally speaking, in mathematics, we let the 0th term be first for no particular reason. I mean, if you want to, you can start with A1. It doesn't matter. I'm just going to call it A0. Then the next term would be A1, the next term would be A2, then A3, and A4. Now, one way of writing the infinite sum is just to put ... like this. Okay, I mean, that is valid. It kind of looks a bit silly. As mathematicians, we don't really do that kind of stuff because, well, there's some kind of implication there. It's not really tidied up. We just don't really do that. I mean, you can write something like this as an intermediate step by all means, and usually when you have infinite series, you want to do that to see what's going on. But another way of writing something like this is we're going to use the Greek letter sigma, which looks like this. And now I'm going to introduce this idea of a counter. Let's use R. It could be any letter, it doesn't particularly matter. And that counter will start at 0 and it'll end at infinity. Okay, so we start at 0, go to infinity. So what we're doing here is we're summing up AR. So when R is 0, we've got the first term. When r is 1, then we've got a1. When r is 2, we've got a2, and so on. And this sigma is just summing up. Now, I've said before in previous videos on the channel, if you like to think about it, sigma is like an S in Greek. It's not really, but S, sigma, S for sum. Now, the comparisons are that if capital A looks like this and little a looks like this in the English alphabet, then for Greek, then capital sigma would be what you're seeing down there, and little sigma like that would be, as I said before, for the standard deviation. Could be a temperature, could be lots of other things. Well, not just temperature. Well, yeah, it could do. The point is, it's risk. It could be anything. Depends on the context of what we're talking about. But it's just a letter, okay? And generally speaking, this R is what's called a counter. And this number here is when we start counting, and the number or concept at the top is where we end the count. Okay, so that's saying starting from 0 to infinity, we're going to add. By the way, just as a side note, it doesn't have to be a series like this. It could be a product. For example, if I had A0 times by A1 times by A2 times by A3 and so on and so on, then this would be P. It'd be pi. It would look like that, pi, where R goes from 0 to infinity of AR. Okay, and the reason for that is because pi is, well, it's the closest we have to a P, and it's P for product. Okay, this S, sigma, S for sum, because we're adding them, and P for product. This product notation for infinite products, we don't really see at A level, which is a shame. You might see it on a step paper. In fact, I remember a couple of papers where they've introduced it, but they've often explained what this notation means. And in general, leaving your answers in the form of an infinite product or a product up to a certain way is still valid. Although I wouldn't do it for A level. For beyond A level undergraduate stuff, yes, it's perfectly valid. So suppose I wanted to evaluate something like this. Let's suppose I wanted to evaluate the sum from R is 1 up to say 5 of, let's say, 2 lots of R minus 1. Okay, let's say I wanted to evaluate that. Well, the first term is when R is 1. So what is 1 minus 1? That's 0 times by 2. So we've got 2 times 0. Plus next term, when R is 2, I've got 2 minus 1, which is 1 times 2. Plus, and then when R is 3, the third term, I've got 3 minus 1, which is 2 times 2. And then when R is 4, I've got 4 minus 1, which is 3 times 2. Add that on. Plus, and then when R is finally 5, I've got 5 minus 1, which is 4 times 2. Now, I'm hoping you can see that this will just sum up to 20. The other thing I wanted you to see is that if I have a constant, a multiplicative constant in that sum, and it's not affected by the R in any way, shape or form, I can take that constant out as a factor. Do you agree that this series is the same as the sum from R goes from 1 to 5 of R minus 1, and I just take 2 out as a factor, because this will be 2 lots of 0 plus 1 plus 2 plus 3 plus 4, which is still 20. Okay, that's totally fine. Okay, so just like with integrals, I can take this out. In actual fact, that's an interesting case. With integrals, y by dx, if I have a ky there, then I can take this k out as a factor. I've already said this. That is because integrals are essentially the limit as a change in x tends to 0 of an infinite sum of y's times by that delta x. So in actual fact, we can take it one step further. K times by the sum of that y delta x. And we can actually go even further. This k is not being limited by the limit as delta x tends to 0. So it's actually k times by the limit of delta x tending to 0 of the sum of y dx. Okay, so there's quite a lot to take from that. You just have to take it case by case, but generally speaking, multiplicative constants can be taken out or rearranged as much as you want to, as long as they're being multiplied and as long as they don't depend on the counting function. So for example, let me show you an example where that wouldn't be true. Let's suppose I have a similar thing. I have the sum from r goes from 1 to 5, say, but this time I've got an r minus 1 and it's times by 2 to the r. Okay, now that wouldn't, I can't take that out because that 2 to the r, that 2 term being multiplied by r minus 1, that has got an r involved, which is associated with the counting thing. So there's no real trick to here. Well, there is, but we'll get to it. You just write it. We'll get to it in another video when we look at sequences and series in general. But again, for the first term, I sub in 1, so it's going to be 2 to the 1 times by 1 minus 1, which is 0, plus. And the second term is going to be 2 to the 2 times by 2 minus 1, and then so on and so on, and you just evaluate that to whatever that is. Okay, so it's fairly straightforward. Okay, so you need to have a little bit of understanding of what sigma notation is, what pi notation is for later on, although I'm not really going to be talking about it until later videos, especially on the Tuesday and Wednesday geometry, vectors and calculus videos that I'll be making. So I've got a couple of examples. You can pause the video, you can give it a go yourself. I'll go through it in a second. So, what have we got here? We've got a sum from 1 to 48 of these logs of base 5s of n plus 2 over n plus 1, where n is the counter, and we've got to show this equals to 2. Okay, now I've done another video on logarithms, and if you want to check that out, when did I do that? I believe I talked about logarithms on the 13th of April, a while ago. Yeah, but it's always good to remember log rules, they're always good. So what have we got here? The first term is when n is 1, so I've got log base 5 of 1 plus 2, which is 3, over 1 plus 1, which is 2, plus. So I'm just going to put sigma there instead of writing it out. We know what sigma means. Sigma is the sum. When n is 2, I've got log base 5 of 2 plus 2, which is 4, over 2 plus 1, which is 3, plus, and then the third term is going to be log of base 5 of 3 plus 2, which is 5, over 3 plus 1, which is 4, plus, and so on and so on and so on. And then the last term is going to be log base 5 of when n is 48, I've got 48 plus 2, which is 50, over 48 plus 1, which is 49. Okay, so let's remember our log rules. And our log rules are that log of A plus log of B equals log of A times by B. Okay, so when you add logarithms together, you multiply the arguments. So what's going to happen when we add all these logs together? Well, this sigma is going to be log base 5 of 3/2 times by 4/3 times by 5/4 times by, and so on and so on. And the last thing we multiply by is 50 over 49. Okay, is there anything that strikes us odd about this? Well, look, these 3's will cancel, the 4's will cancel, And it looks like all these diagonals will cancel until the very last term, by which we'll only have a 50 on the top and a 2 on the bottom. So we're now going to have our sigma is going to be log base 5 of 50 over 2, which is the same as log base 5 of 25. And if you remember logarithms, the way it works is the base 5 to the power of what equals the bit in the middle, the argument of that logarithm. Well, 5 to the what is 25, the answer is 2. And that is exactly what we needed to show. Couple of points. Notice how with this terms cancelled, and what we call this in particular is we call this a telescoping series, a telescopic series, because if you imagine a telescope, you know, with its individual parts like that. Oh, I've done this particularly wrong. Then imagine the telescope was particularly long, and then you can squish it down into a single bit, right? So there's no particular reason why it's called a telescoping or telescopic series, other than all the terms kind of cancel and it shrinks down like a telescope. Generally speaking, when you're trying to evaluate sums, you want to look for shortcuts, you want to see if things cancel. It's kind of like when you're cancelling fractions, really. There's no always be on the lookout for this kind of thing and so on. You just have to do it case by case. However, there are a couple of little tweaks that help you get around that. And one of them is called the methods of differences, which we will cover later on. But that's getting a little bit sidetracked from series expansions that I want to talk about today. The point is, if you can spot a series, well, this isn't technically a series because it doesn't go on to infinity, but at least it gets you into the flavour of sigma notation. Okay. Next question, if you want to pause the video. A sequence where U1 is the first term, U2 is the second term, U3 is the third term, and so on, is defined by the next term equals 1 over the term before, where the first term is 2/3. Find the exact value of the sum from 1 to 100 of UR. If you want to pause the video and give it a go yourself, I'm going to go through it in a second. Okay, so find the exact value of the sum from 1 to 100 of UR. So let's just see what happens after a couple of terms. Well, if U1 is 2/3, then what is U2? Well, U2 is the reciprocal of that, which is 3 over 2. And then when I want to know U3, I flip that U2 and it becomes 2/3 again. And it's just going to keep going backwards and forwards. This is an oscillating series. It's going backwards and forwards. It's not particularly converging or diverging. It's just oscillating. So what happens if I were to add 100 of these terms? Well, I would have 2/3 plus 3/2 for the first two, plus another 2/3 plus 3/2, plus and so on and so on. And I would have this stuff going 50 times. Why? Because they're in pairs, and there's 50 pairs in 100. So all I need to do actually is just add these two together, and whatever that result is, times it by 50. So thirds and halves, let's make those sixths. So if I times the left one by 2 top and bottom to make them to sixths, that's 4/6. And then 3/2, if I times by 3 top and bottom, is 9/6. So 4/6 plus 9/6 is going to be 13 over 6. And now I need to times that by 50. So the 50 and the 6 will cancel to 3 and 25. So the answer is this sum will be 25 times 13 over 3. What is that? Well, 25 times 4 is 100. And there's 3 4s into there. So I believe that's 325 over 3 as a top-heavy fraction. Yeah, because 12 25s are 300. There's one extra 25, so that makes 325 over 3. Yeah, not a lot you can do there. Okay, right, now on to the main bits. Binomial expansion. So we're going to recap some year 12 stuff, um, or learn some new year 12 stuff if depending where you are. So what is a binomial? A binomial is just where you have, bi just means two, and nomial is just terms or numbers. So an expression that has two terms is a binomial. So let's take a really easy one. Let's say 1 plus x. Really easy. So if I wanted to expand 1 plus x, that's easy. That's just 1 plus x. If I wanted to expand 1 plus x, let's say squared, then using FOIL or expanding double brackets, you should get 1 plus 2x plus x squared. And then if you're feeling braver, 1 plus x cubed, you should get 1 plus 3x plus 3x squared plus x cubed. And then if you can find 1 plus x to the power 4 and you expand it, then that'll be 1 plus 4x plus 6x squared plus 4x cubed plus an x to the 4. Now, you're probably thinking, okay, how can you rattle those through quite quickly? Well, there's various reasons. One, people that are familiar with this stuff will remember something called Pascal's triangle. And if I just write it side by side, so 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. You're probably thinking, okay, so I spot there's 1 there and 1x, that's 1, 1. There's 1 there, 2 and 1x squared, so that corresponds to 1, 2, 1. There's 1 there, 3, 3 and 1, so that corresponds to 1, 3, 3 and 1. And this is 1, 4, 6, 4, 1, and this is 1, 4, 6, 4, 1. And you're probably thinking two questions. One, where is that extra 1 at the top coming from? And that actually is what happens when you get 1 plus x and you raise it to the power 0. Because anything that's not 0 raised to the power 0 is just going to give 1. So that's where that one comes from. The second question you're asking is like, right, okay, so how do you generate this triangle? Well, if you haven't seen before, it's very simple. To get a number, you have to look diagonally up right and up left and add those two together. So to get that 2, we've added the 1 and 1 together. To get this 6, we added the 3 and 3 together. So if I wanted to generate the next row, I've always got 1s on the outside. And 1 and 4 will make 5, 4 and 6 will make 10, 6 and 4 will make 10, and 4 and 1 will make 5. And not quite, but you can imagine there's like a line of symmetry here. Okay? So if you get something like 1, 5, 10, 12, 5, you've made a mistake. It's almost semi-symmetrical. Okay, now you're probably thinking, right, okay, so how is that going to help? Well, in actual fact, let's actually look what's happening when we do a binomial expansion. And let's look at the 1 plus x cubed case, because that's, well, yeah, okay, let's do that. So 1 plus x cubed. Well, what is that? That's 1 plus x times by 1 plus x times by 1 plus x. Okay, and the technique we use to expand all of these brackets is we choose one element from those two, and we have to consider every combination of multiplying by a different element in another bracket. And there's quite a few. If you think about what we did for 1 plus x squared, which was 1 plus x times by 1 plus x, then the acronym FOIL, first, outer, inner, last, is a good way of making sure that we get all four combinations. However, for 1 plus x cubed, we just have to be careful and make sure we get every single combination. So, whoops. Is there a quicker way? Well, I've alluded to this on my other video. I believe it was my first recreational and entrance exam techniques on Sunday the 19th of April if you wanted to check that out. And essentially what we're going to be looking at is, suppose I want to isolate terms at a time, i.e. I'm interested in the constant terms. Well, put it this way, let's assume that out of my 3 brackets I want to choose my x's. So out of 3 brackets I want to choose 0 x's. And that's how many combinations it will be for the constants. And then what happens there is the only way to get a constant is just going to be the 1 times the 1 times the 1. So that would be 1 cubed, and I'll have x to the 0 because I don't have any x constants. For the next term, I want to choose the amount of x's. So that would be out of 3 brackets, choose 1. And now what happens when I have x terms? Well, I'm going to have one x term times by a 1 and another 1, or I'll have this x term times by that 1 and that 1, or I'll have this x term times by that 1 and the other 1. So I'm just going to have 1 squareds, 1 times by itself twice, and then x to the 1. Now, the reason why that these powers must add up to the number of brackets is because you're taking one term from each bracket. So what we're saying is we want the combinations of picking 3 1s from a bracket and no x's. So each one bracket has taken a 1 from it. So that's 3 1s. So it's 1 times by itself 3 times. And you can apply this logic as you go on. So the next will be 3 choose 2, and that'll be 1 to the 1 now because we only want 1 1s, and the others are going to be 2, so 2 2s. And then for the final bracket, it's going to be 3 choose 3, i.e. out of 3 brackets we want all 3 3s because that'll be x times x times x, which is the x cubed, and we want to pick no 1s, so that'll be 1 to the 0. And in actual fact, this is the binomial expansion in combinatorics form for 1 plus x cubed. Okay, now I just want to remind you, if you haven't seen the previous video, is when I write 3 choose 0, I'm saying 3 choose 0 objects. Now there's a button on your calculator that will say C. On most calculators, it's above the division symbol. So you have to press Shift and then divide to get that C button. If you have the Casio CG50, where do you need to do? There's a couple of ways. You can either, if you've got the CG50, you can either press F4 for math, and then press the Option button, and then you can press F1 for list. Oh no, not that one. Where is the list? No, there is a way. Where is it? Ah, there it is. Right, what you do is you press, for the CG50, you press F4 for math. You then press the Option button. You scroll to the right. Then you press F3 for probability. And then it's F3 again for NCR. It will look like the NCR button like that. Now, if you want to know what's going on here, N choose R means we're choosing from N objects. We want to choose R of them. And the calculation for that is N factorial over R factorial times N minus R factorial, where factorial means that if I was to take 3 factorial, it'd be 3 times 2 times 1. If I was to take 5 factorial, that's 5 times 4 times 3 times 2 times 1. And I've said before, factorial is just for whole number things, and you multiply by descending integers. if you're interested in factorials of non-integers, then you might have to look at the gamma function. So if I wanted to say gamma of a half, for example, I will cover that in a later video, but it involves calculus that you're not quite ready for, multivariable parametric calculus, which you're definitely not very ready for. But I will talk about it at some stage. But the point is, check out my UKMT kangaroo problems from the 19th of April of when I'm talking about counting strategies, if you want to recap on that. Okay, so from year 12 stuff, you should be able to expand binomials when the power is a whole number and you can just crunch it out like so. So for example, let's pick a nice juicy year 12 problem. Let's say I've got 2 minus 3x and I want it to the power 5, and I want say the first 3 terms in ascending powers of x. Okay, so we're going to have 5 choose 0 of no x's, so everything is the power 2. And I could write minus 3x to the 0 if you wanted to. Please be careful with the sign. Plus 5 choose 1 of 2 to the 4, and now this is minus 3x to the 1, plus, and then I wanted the first 3 terms, so one more term, so this is 5 choose 2 of 2 to the power 3 times by minus 3x squared. There are other terms, but we'll leave it as that. Okay, let's crack on. So 5 choose 0 is 1, because another philosophical way of asking that question is, I've got 5 objects, how many ways are there of choosing none of them? Well, there's just one way, don't pick anything. And by the way, if you're curious, and I did say in the other video, 0 factorial is 1. The reason for that is because you can play a game, for example, 3 factorial is just 4 factorial over 4, 2 factorial is 3 factorial over 3, 1 factorial is just 2 factorial over 2, and then by similar definition, 0 factorial is just 1 factorial over 1, and that's perfectly defined. You can't go into negatives, because if you kept playing that game, minus 1 factorial will be 0 factorial over 0, and dividing by 0 causes a few confusions. Anyway, so back to here. So 5 choose 0 is 1. 2 to the power 5 is 32. So it looks like 1 times 32 times by another 1. So it looks like the first term's 32. Plus, now 5 choose 1 is also easy to sort out, because how many ways are there of picking one object from 5? Well, there's 5 different ways. You either take each one. So this is going to be a 5. 2 to the 4, I believe, is 16. And minus 3x to the power 1 is just minus 3x. So what is 5 times 16 times minus 3x? So 5 times 16 times minus 3. I will get, actually, negative 240x. Okay, and for the next one, I've got 5 choose 2, which is a little bit difficult. So 5 choose 2 is 10. If I times that by 2 cubed, which is 8, and then I times that by minus 3 squared, careful, the minus 3 squared becomes positive, times by 9, this will become 720x squared. Okay, so the first 3 terms for 2 minus 3x to the power 5 is 32 minus 240x plus 720x squared. Let's take a breather from that and just reflect a few things. One, I am not estimating anything at this stage. The first 3 terms from this expansion, this binomial expansion with an integer power, is 32 minus 240x plus 720x squared. There has been no cause for alarm. There's no need for checking if things work or not. You can almost fly headlong into danger and be totally fine. However, let's look at some year 13 binomial expansion. let's suppose, now I had this very strong stipulation, this only works for when this power belongs to the set of positive integers, right? Now I'm going to let n belong to the set of quotients, rational numbers. That is a terrible Q, italicized. Whoop, 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 whoop. There you go, much better. So now, for when n belongs to the set of rational numbers, so this is positive, negative, even 0, and so on. So, right, let's take it one step at a time. Let's suppose we have no, we don't really care. Well, let's say I've got a plus b, and I don't particularly care what the power is. Right? Let's go off in the way that we normally would have, i.e., n choose 0, and then I've picked no b's. This would be a to the n, and then times by b to the 0, plus, and then we carry on in the usual way, n choose 1, a to the n minus 1, and this is b, not 0, this is b1, plus, and then the next term would be n2, and then this would be a to the n minus 2, and then this would be b to the 2, and so on and so on and so on. Right, now here's the problem. This choose stuff is what's causing the problem. Raising things to the power of fractions or rational numbers is totally fine. That could be done if n was a fraction. This could be done if n was a fraction. The problem is these combinatorics thing, because we can't really deal with the factorialness, if that's even an adjective, for when it's not an integer. So let's try a different way. So we're going to look at the definition up here of what n choose r actually is. So what have we got? N choose 0, if you think about it, is n factorial over 0 factorial times by n factorial, which is n minus 0. So what's going to happen? The n factorials cancel, 0 factorial is 1, so this thing just becomes a fat 1. So already we're going to have 1 times by a to the n times by b to the 0. That's nice. That term is a-okay, there's no factorials in there, we're cool. N choose 1, well that's going to be n factorial over 1 factorial times n minus 1 factorial. And now let's think carefully a little bit. N factorial is the same as n times by n minus 1 times by n minus 2 and so on, which is the same as n times n minus 1 factorial. So that factorial and that factorial cancel. 1 factorial is just 1, so we're just left with an n. So this becomes n lots of a to the n minus 1 times by b to the 1 plus. And now we've got n choose 2, so we're going to have n factorial. We'll do that bit last because you'll see what happened. On the bottom we're going to have 2 factorial and we're going to have n minus 2 factorial. Now if I want that n minus 2 factorial on the bottom to cancel, what do I have to times n minus 2 factorial so I get n factorial on the top? Well, that must be times by n minus 1 and then another n. So this and this will cancel. The 2 factorial is just 2, so that can go. So now we have n times by n minus 1 times by over 2, which is 2 factorial. And then this will be a to the n minus 2, and this will be b squared. And now, if you look at this, this is totally fine. N can be anything. We're not going to be gazumped by factorials raining on our parade. Now, there's one more tweak to this. Instead of a, to make things easier, let a equal to 1. So then what will happen is the a's are just 1s, so anything to the power 1 is just 1, so we don't need to put that there. So that disappears, and that disappears. Let's move these together a little bit. And b to the 0 is just 1, so that's just done, that can go. So now we have such a nicer, neater form of the binomial expansion. Right, so let's have a look here. If I have 1 plus ax now to the n, this is going to be 1 plus n lots of this part, which is ax, plus n times n minus 1 over 2 factorial, because remember that 2 factorial didn't cancel, and this will be ax all squared, plus, and then can we guess what the next term would have been? Well, it would have been n times by n minus 1 times by n minus 2, right? Because we kept, it would have gone down the factorials. Look, it goes from n to n minus 1, and then it would have been the next one because the factorials would have cancelled. And then on the bottom, there would have been 3 factorial. And then this would have been ax all cubed. And we could have kept going like that. Okay. Now, here's the next part. There's 2 things. When n was a whole number, for example, like 5, like 6, like 7, and so on, we knew when to stop this, right? We knew when to stop this. For example, when it was 1 plus x squared, we knew we'd get 1, 2, 3 terms. When it was just 1 plus x, which is the 1, we're just going to get 2 terms. There was always one extra term. Now the problem comes from what happens when n is 1/2. Does that mean there's going to be 3/2 terms? Well, that just doesn't make sense anymore. In actual fact, what's great about this is that you can go on forever. You can go on forever. Here's the problem though. This thing, if you go on forever, is a series. However though, this is definitely finite. And you have to resolve this in your own head. How can an infinite series equal a finite sum? And the truth is, only in very special circumstances. And the way we deal with that is we say, okay, this is only a finite series when, now this is really important, when this ax term here is less than 1 or greater than minus 1. Now another way you can write that is we can say the magnitude or the length of ax is less than 1. Now here's the reason why that has to be the case. Because the first term, if that, okay, next up, do you agree that if I take ax and I raise it, that ax squared is going to be smaller than ax if ax is trapped between 1 and minus 1? And do you agree that if I was to cube it, that would be even smaller? And then if I was to raise it to the 4, that would be even smaller, and so on, and it would eventually tend to 0. Now, this convergence, if ax is less than 1 but greater than minus 1, means that for more and more terms, the terms contribute less and less and less. And it'll get to the point where you're essentially adding 0. And at that point, when it's reached to such a small amount, the series has converged and it has reached a finite limit. However, if ax was greater than 1, look what happens. Well, then ax squared is bigger and ax cubed is bigger than that, and so on and so on. These terms are just going to blow up to infinity, and that isn't necessarily the case when n is a finite number, and thus this expression, this binomial over here, is finite as well. It's just not going to work. So this binomial expansion, I'm hoping intuitively you get, only works if this term, the ax term, is between 1 and minus 1. Now there's the second caveat here. This only works when there's a 1 in front of it. Okay, so let me go through a couple of examples of what to do if that's not the case, and how to tell when something converges or not. So say for example I've got the following. Let's say I've got 4 plus 9x and I've got this to the power of a half, and I want to expand it for the first 3 terms. And you could do this for 4 terms or 5 terms, as many as you like. There's an infinite amount. Right, now what you have to do is you have to turn this 4 into a 1 somehow. So if you take 4 out as a factor inside this bracket to the half, then I've got 4 lots of 1 plus 9/4 of x. And now what you can do is you can take the 4 out of this bracket, but be careful, this to the power half is still in effect. So you're going to have 4 to the half times by 1 plus 9 over 4x, all to the power half still. And now you can just evaluate this. So 4 to the half, well, that's just 4 square rooted, which is 2. So now what this is telling me is the binomial expansion for this original thing is just going to be 2 lots of the binomial expansion of this thing. So this is going to equal 2 lots of. And now this is relatively straightforward. Remember our binomial expansion for this was 1 plus nax plus n times n minus 1 over 2 factorial times ax squared plus and so on and so on. So all I have to do is do n times ax. So a half times 9/4 is 9/8. Sorry, first term first, 1 plus nax, which is going to be a half times 9/4, which is 9/8 of x, plus, and now when n is a half, I'm going to have a half times by a half minus 1, which is minus a half, all over 2. And then I'm going to have to multiply that by ax squared, which is 9/4 x all squared. Be careful. I've got a half times, well, what's the sign first? I've got a positive times negative over a positive times by a positive, so it's going to be a negative. On the top, I'm going to have 1 times 1 times 9 squared, which is 81, all over a 2 times 2 times 2, which is an 8, times by a 4 squared, which is 16. So 8 times 16, I believe, is 128. And then this will be x squared. Dot, 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 dot. So the binomial expansion for this, I just need to times everything by 2 to get 2 plus 9/4 of x minus 81 over 64 x squared. So the first 3 terms of 4 plus 9x to the half, I'll get 2 plus 9/4 minus 81 over 64. And this is only valid when this thing is trapped. This is only valid when 9/4 of x is trapped between 1 and minus 1. So if you want values of x to know what that's going to mean, I can times both sides by 4 to mean that 9x is trapped between 4 and minus 4, and divide by 9 to show that x has to be trapped between 4/9 and minus 4/9. So if I wanted to approximate, say, the square root of 4 using my expansion, so I've got 4 plus 9x to the half. This is clearly when x is 0, because then I have 4 plus 9 lots of 0, which is 4 to the half. And according to my expansion, when x is 0, I'll have 2 plus 9/4 of 0 plus minus 81 over 64 lots of 0 squared, so it's minus a 0. And clearly that's quite a good approximation. However, let's try a more interesting example. Let's suppose I wanted to work out, well, let's suppose somebody wanted to work out the square root of 13. So in that case, I'd have to use x is 1. Now, because x is 1 is outside of this convergence radius, then we shouldn't really do that. So do not use. Or rather, it's just not particularly accurate. For example, let's try that. Then we're saying the square root of 13 apparently is 2 plus 9/4 of 1 minus 81 over 64 lots of 1 squared. So if I do that, I'm going to have 2 plus 9/4 minus 81 over 64. And that's 2.9 84375, and if I compare that to the actual square root of 13, the actual square root of 13 is in the region of 3.6055 and so on, and clearly these two numbers do not agree with each other at all. Really, you have to stay within these. This what's called a radius of convergence. Now, because we only did the first three terms, it's not a problem. But if you were to do an infinite amount of terms, then because x is bigger than 4/9 and x is 1, then technically, for our expansion, this would tend to infinity. It's unbounded. There's no upper limit. You just keep going, you just keep adding larger and larger values of x. And clearly the square root of 13 is not an infinite number. It has to converge. Okay. So, I think that's pretty much it for binomial expansion. I'll go through a couple of examples. If you want to try them yourself, that's absolutely fine. So, pause the video, give yourself some time to do these questions. Okay. Use binomial expansions to show that the square root of 1 plus 4x over the square root of 1 minus x is approximately that. Okay, well, in this case, we're going to have to combine some things. It's interesting because you could either do some algebraic long division, or you could do the binomial expansion for each ones and then multiply them together. Well, let's just do them individually. So I've got 1 plus 4x to the power of a half, and then that's over 1 minus x square rooted, so that's actually 1 minus x to the power of minus a half. Now, because I'm only interested in up to the x squared, I'm only going to do up to the x squared term for each one. And because these are nice and they start with a 1, I don't have to do any fiddling. So they're both going to be 1 plus n times that, so a half times 4x, that'll be a 2x. And then minus a half times that, that'll be plus half of x. And then the next term will be n times n minus 1 over 2 factorial. So that'll be a half times by minus a half over 2, so that'll be minus an eighth for the top one, times by 4x all squared, which is going to be 16x squared, times by minus an eighth. So I believe that's going to be minus 2x squared, because 16 divided by 8 is 2, and there's a negative there. For the next one, I've got n is minus a half, but then I have to times by n minus 1, which is minus 3 halves, and this is all over 2. So the minus minus will make a plus, so I know that's positive. And then I have a minus x all squared, which is still positive. So I'm going to have 3 over 8, so that's going to be 3/8 of x squared, and so on. Now, since these two are being multiplied together, I'm going to have to multiply these two things. The reason why I don't have to include the x cubed terms is because if I consider x cubed times by anything else, it's going to give me an x cubed term or higher, and I only care about the x squareds. So really, I only have to consider up to the x squareds. Right, let's deal with the numbers first. So let's call, well, it is the square root of 1 plus 4x all over 1 minus x. This is approximately equal to. Now the numbers terms, it's only going to be 1 times 1. I can't do 1 times anything else because that's going to involve x's, that's not going to work. So that's a 1. Right, now let's consider all the x terms. Well, I could have a 2x times 1. Those two would time together to get an x, and a half times that would times together to get an x as well. So 2 plus a half is 2.5, which I believe is 5 halves. So that becomes 5 halves of x. And just scrolling up, yep, we've got plus 5 hex over there. Right, next up, where would the x squared terms be? Well, we'd have a 2x times a half x, that's one combination, so we're going to have a 1. We'd have a 3/8 times 1, because if we had 3/8 x squared times 1, that would also be it, so plus 3/8. And then the other combination is the 1 times minus 2, so we'd also have a minus 2 popping out there. Common denominator time, this is 8/8 plus 11/8, 3/8, sorry, is 11/8, and minus 2 is minus 16/8, so this is clearly going to be minus 5/8, so I believe there's minus 5/8 of x squared in the last term. And yes, that's exactly what we needed to prove. Okay. Right. A student substitutes x equals a half into both sides of the approximation shown in part A in an attempt to find an approximation for root 6. Give a reason why the student should not use x equals a half. Okay, let's have a look at each of these sequences, each of these binomial expansions to see what needs to happen. So for the first one, the radius of convergence is going to be 4x is less than or equal to 1 and minus 1. And then for the second one, this minus x, if you like, has to be between 1 and minus 1. But then if you divide by minus 1, that's essentially going to make that. Now, if I look at the right-hand side, that's okay. But if I look at this left-hand one, if I divide by 4, x has to be less than a quarter, but greater than minus a quarter. So if I was to put this on a number line, then this inequality region, if that's 0 and that's a quarter, half, 3/4, 1, minus a quarter, minus a half, minus 3/4, 1, then this is satisfied by empty dot, line, empty dot. And if I was to look at this radius of convergence, this goes from a quarter down to a quarter. And now I can only substitute in x values which satisfy both, and clearly both are satisfied in this region here, which is where x is between a quarter and minus a quarter. So substituting x equals to a half is not a good idea. You can say the radius of convergence is between x is less than a quarter, x is greater than minus a quarter. You could say the series of 1 plus 4x to the half diverges for values greater than a quarter, and a half is greater than a quarter, and so on and so on and so on. Okay, for the next one, part C, substitute x equals 1 over 11 into this to obtain approximation to root 6. Okay, so what happens if I sub 1 over 11 into the left-hand side? Well, let's deal with that over here. So square root of 1 plus 4 times 1 over 11, so that's going to be 4/11ths, over 1 minus x, which is an 11th. Okay, so what does this simplify to? So it's the square root of 1 plus 4/11ths, I believe, is 15/11ths, over 1 minus 1/11th is 10/11ths. The 11ths can cancel top and bottom, so this is the same as the square root of 15 over 10, which to me simplifies down to root 3 over 2. Interesting. We want root 6 out of this, do we? Okay, interesting. So, think about it. What do I have to times the root of 3 over 2 by, so this becomes root 6? Well, if I times this thing by 2, it will become a 3, and if I times it by 2 again, then it will become a 6. So I have to times it by root 4, and root 4 is 2. So 2 lots of root 3 over 2 does actually equal root 6. So what I need to do, what this is telling me, is if I sub 1 over 11 into my expansion, I will get the root of 3 over 2, and then I have to multiply whatever I get by 2 so that it becomes root 6. So this means root 6 is going to be 2 lots of my expansion, which is here when I sub in 1 over 11. So 1 plus 5/2 of 1 over 11 minus 5/8 lots of 1 over 11 squared. Okay. Right. So in its simplest form, so root 6 is going to be 2 lots of 1 is 2, plus 2 lots of 5 over 2 is 5. 5 times 1/11th is 5/11ths. 2 times minus 5/8 is minus 5/4, and this is times by 1 over 11 squared, which is 1 over 21. Right, so I'm just going to cheat and bung this into a calculator instead of doing it the long way. 5 over 4 times 121. So this apparently is 1183 over 484 as a simplified fraction. And just as a precaution, that is approximately 2.444. And if I was to do the square root of 6, just out of curiosity, that gives me 2.449. So it's not too bad. The first two decimal places are correct. If you want to work out the percentage error on that, knock yourself out. But it's not a bad approximation. Yeah, it is what it is. And it's valid. Okay. For the next question, it's a bit juicy. I believe this was last year's A-level paper question. If you want to have a read of it, make of it what you will. Pause the video, give it a go yourself. Okay, find the first three terms in ascending powers of x of the binomial expansion of that thing. So that thing we can write as 4 minus x to the power of a half, which is the same as 4 take out factor, so that's 4 to the half, and that would be 1 minus x over 4 to the half. To the negative half, sorry. God damn, that's the minus half. Yes, okay. Which is the same as 4 to the minus half is 1 half lots of 1 minus x over 4 to the power of negative 1 half. So immediately I can tell the radius of convergence is when x over 4 is trapped between 1 and minus 1, which means x has to be between 4 and negative 4. We cannot have values outside of that being inputted. Okay, so the expansion can be used to find an approximation to root 2. Possible values of x could be substituted into this expansion are x equals minus 14. Lol, that's a fat lols, that's way outside of minus 4 to 4, so that's just dumb. X equals 2, yep, that's between 4 and minus 4, so that one would be okay. And x equals minus a half, yep, that's between 4 and minus 4, that's okay. Without evaluating your expression, state giving a reason which of these three values should not be used. Well, lol, it's here because the series does not converge. It's not within the radius of convergence, whatever reason you want to give. BII, state given a reason which of these three values of x would lead to the most accurate description. Right, now let's go back to a previous example. When was it? It was here, was it? Do you remember when I let x equal to 0, all of these terms cancelled and I got the true root of 4, which I wanted. It's when I start adding x terms in that it started becoming bad. It wasn't so accurate. Essentially, the closer x is to 0, the more accurate this is. And the reason for that is because when you square things or cube things or raise things to a power for which they're closer to 0, then each of these powers tends to 0 quicker. And therefore, you don't need as many terms for this series to tail off and die off. It approaches a more accurate representation quicker. So the question becomes, which one is nearer to 0? Is it 2 or minus a half? So clearly minus a half is the one that's nearer to 0. So state given a reason which of the three values would lead to the most accurate approximation to root 2. It's the x equals minus a half one that you'd use because the series would converge quicker as each term would approximate 0 quicker. Do I actually need to evaluate this? No. Cool. Happy days. Right. Taylor and Maclaurin series. Right, I need to spell that properly. Maclaurin. Now, sometimes when you hear on YouTube or whatever, you hear them say McLaren, like race car McLaren. It's not McLaren, it's Maclaurin. Maclaurin. Like, not like chlorine, chlorin. Like bin, dustbin, rin, Maclaurin. It doesn't matter if you mispronounce it. If you just say Maclaurin series or Maclaurin series, people will get it. They know what you're talking about. I don't think anyone is to the point of being a Nazi where they'll just say, "Oh, you're not saying it right. I don't take you seriously." You know, it's a thing. Right. Now, what we've been doing so far has been working brilliantly for binomials. We can deal with binomials where they are of the form 1 plus ax to a particular power. Now what I want to look at is real functions in general. Now it won't be too general because, well, I say real functions. They have to be analytic, and I'll talk about more what that means. Essentially, they have to be smooth, continuous. They have to be differentiable everywhere. You know what? That's the most important thing. They have to be differentiable, and they have to be infinitely differentiable. So an example of that would be, let's say, sine of x differentiates to cos of x, and that would differentiate to minus sine of x, and that would differentiate to minus cosine of x, and we're back round again. And because we can keep going round this loop over and over and over and over and over again, we can infinitely differentiate it. Then yes, we can express sine of x as a Maclaurin or a Taylor series. Right, now there's so many good videos explaining why the Maclaurin series and the Taylor series work. But what I want to get into a nutshell is I want to turn real functions, and I want to turn them into infinite sums or series of polynomial functions. That is essentially all I want to do. That is all Taylor and Maclaurin series what it does. It takes real functions and turns them into polynomial functions. Okay, so I'll tell you what, let's just do one. Okay, let's say I've got sine of x. Okay, and I want to turn this into a polynomial function. What do I know about this sine of x? Well, it goes like this, it wiggles, it wiggles, it wiggles. And all I know really, or all I need to know, is that when x is 0, sine of x also equals to 0. That's fine. So if I was to approximate this with a polynomial function, let's say sine of x equals to x, then at the very least, the y equals x graph will look like that. I should draw this better. So, oh, that's terrible. So, at least in the region of x equals to 0, y equals x does seem to approximate sine of x. Okay, now, what information about sine of x can I use to build it up? Well, I know that if I differentiate sine x once, twice, I get itself. So can you think of a function that if I differentiate it twice gives me x? Well, that's easy. All I need to do is just integrate x twice. So x integrated becomes x squared over 2. And then if I integrate that, well, plus a constant. And then if I integrate that again, I'll get x cubed over 3 times 2, which is 3 factorial, plus another function of x, plus a different constant of integration. Now, here's the deal. This cx stuff doesn't interest me so much because I've already considered the amount of x's I want. That's totally fine. I don't want any other x's. I've got my x's, that's fine. However, and then this d thing isn't particularly useful either because I know that y equals x plus a number isn't going to work because that means my straight line, which is this red thing, if I can highlight it, it's just going to be shifted up, so it's not going to work. However, the new bit of information is this x cubed over 3 factorial. That's amazing. The problem is that now has to be negative because I want it to be negative sine of x. So the next term should be x cubed over 3 factorial. Right? Why does that work? Well, because if I differentiate both sides twice, then sine x will become minus sine x, and the x differentiated twice will go 1 and then to 0, and the minus x cubed over 3 factorial will then become minus x, if you think about it. And that's essentially saying sine of x equals x. But now there's a problem. I mean, that works. That's great, because we initially had sine of x was particularly well represented by x. That's fine. However, there's a slight problem there. By introducing this minus x cubed over 3 term, I now need to have a minus x cubed over 3 term popping down here. Now there's a problem. Because now I have to play the guessing game of like, okay, well, what term should I add here? So when I differentiate it twice, so it goes down there, it's the same as minus x cubed over 3. And with a little thought, it's actually going to be plus x to the 5 over 5 factorial. Why? Let's differentiate it once. That becomes 5x to the 4 over 5 factorial. So the 5 and the 5 factorial becomes a 4 factorial. I differentiate it again. The 4 comes down, so it's 4x cubed over 4 factorial. The 4 and the 4 factorial cancel. I've now got x cubed over 3 factorial. And then after differentiating it twice, that will equal minus sine of x, so I want that to be negative. So that works. If I was to differentiate this whole thing again twice, I would get minus sine x, I would get minus x there, and I would get positive x cubed over 3 factorial, because x to the 5 factorial differentiated twice becomes x cubed over 3 factorial. If I then times top and bottom, if I just times, if I now multiply this bottom thing by -1, that becomes positive sine, that becomes positive x, and now this becomes minus x cubed over 3, and we get the first 2 terms behaving as how they should do. And then we've got to go, okay, well, hold on a minute now, but then you've increased this, and so on and so on. And the idea is, I'll cut to the chase, is we've now essentially got to add an infinite amount of terms so that when we differentiate them, they all shuffle down to form, you know, what we're expecting. And because there is no limit, because we're dealing with an infinite sum or series, then I'm never going to run out of terms to differentiate twice to give negative sign. So I'm A-OK on that front. Now, what you're also probably thinking is like, okay, well, how can I express this in a better way? Well, now that we've got sigma notation, this is the same as the sum from, well, let's go from I is 0 to infinity. Now the first term, well, let's look at a general term like this one. Well, they're clearly odd numbers, x to the 1, x cubed, x to the 5. So how would I write an odd number? Well, I could have x to the power of 2i minus 1. But if you think about it, the first term was 1. So what have I got to do to 0? Double it, and then add 1 or subtract 1. I have to add 1. So at least that's all the x has done. Next up, I have got to consider that it goes positive, negative, positive, and the next term's negative, positive, negative, positive, negative. And the easiest way to sort that one out is do -1 to the power I. Because now -1 to the 0 is just positive, -1 to the 1 is -1, -1 to the 2 is +1, and now it's oscillating between positive, negative, positive, negative, positive, negative as we'd like. The final thing to consider is whatever the power of x was, that's how many factorial we're dividing by. So this 2i plus 1 on the top, we're just going to divide that, so 2i plus 1, and make that a factorial. And now I have got an infinite sequence, an infinite series, an infinite sum, a series of what sine of x is in terms of polynomial functions. And to let the cat out of the bag, any series that starts or is based around x equals 0 is called a Maclaurin series. And the way to sort that out, it's really easy, is if I've got the function f of x, then let's backtrack. What is it that we did? Well, we didn't actually do it for sine of x, but what we need to have is a function where f of 0 is included. Now, since sine of 0 is 0, then technically we've added a 0 here. And then what did we do? Well, we considered how many x's we had. And now, what we want to do is we find the first derivative at 0 and times it by x. And then the next term would be f, and then the second derivative at 0 over 2 factorial is x squared. And then it will be the third derivative at 0 over 3 factorial, then times by x cubed, and so on and so on and so on, as many times as you like. And if you want to, f of x in terms of Maclaurin would be the infinite sum of, from I goes to 0 up to infinity, of f to the I of 0 times by x to the I over I factorial. And that is the condensed form of the Maclaurin series. Why does this work? Because this is x to the 1 over 1 factorial, and this is x to the 0, which is 1, over 0 factorial, which is also 1, and now all the terms behave like this rule says. Brilliant. Now, we say the Maclaurin series is centered about 0. Okay, now that's really important because when we were constructing our Maclaurin series, all we knew was that the series worked around this point 0. Now here's the problem. What if it doesn't? So, for example, what about ln of x, the natural log of x? That doesn't work about 0. That's not going to work. What about sine of x over x? Or if I plug a 0 in there, that's not going to work either. And yeah, generally speaking, not great. Now, what we're going to do is we're now going to talk. This is the Maclaurin. This is the Maclaurin. The Taylor series is more or less exactly like the Maclaurin, but everything is shifted. What we do is we say that the Taylor series, so the Taylor series, that's another key point, the Taylor series is like the Maclaurin, but centered around another point. We can choose any other point we want, and it's going to give us a different Taylor series depending on the point. This is super duper critical, right? So when somebody asks you what's the difference between a Taylor series and a Maclaurin series, you can say, well, the Maclaurin series is an infinite sum of polynomials that expresses a function, but it's centered around 0. And a Taylor series is another infinite sum of polynomial functions, But this time it's not necessarily centered around 0, it could be centered around anything else. So how do we center this about something that's not 0? Well, let's check it out. So, a couple of things. F of 0 and all its derivatives are completely out. We can't do that. What we can do, however, is we can actually do quite a cheeky little substitution. Right? Suppose we shift everything along a little bit. So suppose we're now dealing with f of x plus some tiny amount. I don't know, let's call it a. So then how would that change everything? Well, now we're not dealing with f of 0, we're dealing with f of a now. And, well, let's just do the general thing. This would be the sum from I0 to infinity of f of I evaluated at a, lots of x to the I over I factorial. That's fine. But now I don't particularly want f of x plus a. Let's suppose I want f of, well, let's suppose now that I don't want x plus a, I let new capital X equals x plus a. So now I've got capital X of f equals the sum from I0 to infinity of fi of, now it's still a, that's not a problem. But now I don't have little x anymore. If I look at this substitution, then capital X minus a equals little x. So I've actually got capital X minus little a to the I over I factorial now. And now this is the great thing. Because of this transformation, and because capital X could be anything, let's make capital X little x again. And now I have the condensed form of the Taylor series. Here it is. Now this is great, because now if I can't evaluate the function at 0 for whatever reason, I can now shift that function along and evaluate it at a different point. I can center it around a different point. So this Taylor series is centered at x equals a, and it will be a function of x minus a, and then x minus a squared, and then x minus a cubed, and so on and so on. So let's try an example of that before I do some proper questiony type things. Oops, daisy. Right, okay. So, let's suppose what would be a good Taylor series? Well, let's just pick one. Let's do well, no, you know what? Let's just go through the examples. I don't know why I made an extra page. So, okay. Well, this is a Maclaurin one, and then I think the next one, yeah, that's a Taylor series, and then the last one, that's also a Taylor series. All right, cool. So, if you think you've got those formulas and you'd like to give it a go, pause the video. At the moment, this is Core Pure 2 and FP1 maths, so this is Year 13 maths. If you're finding this difficult, then that's totally fine. I'll go through them in a second. So, given that f of x equals ln of cosine x, so just to be clear, f of x equals the natural log of cosine x. Both these functions I've talked about before in previous videos, and we know how to differentiate them, so that should be fine. Show that f dash of x is minus tan of x. Okay, So for part A, we're going to have to do the chain rule. So f dashed of x is, well, ln of something becomes 1 over that something when you differentiate it, so that's 1 over cosine x, and then that's multiplied by the chain rule, this argument differentiated and brought outside. Cosine differentiates to minus sine of x, so that's okay. If I tidy this up, I've got minus sine x over cosine x, and sine over cosine x is just minus tan of x. And that's exactly what we wanted to show. Okay, part B. Find the values of f dash of naught, f double dash of naught, f triple dash of naught, and f quadruple dash of naught. Okay, so f dash of naught is just when I substitute x as 0 into here. So tan of 0 is 0, so that's a nice one. F double dashed of naught, well, tan differentiates to sec squared when you're used to that. So minus tan will differentiate to minus sec squared of x. So minus sec squared of 0 will just be minus 1 over cos squared of 1. Cos of 0 is 1. 1 minus 1 over 1 squared is minus 1, so that's just going to be minus 1. I like to put brackets around it to remind myself where the answers were. F triple dashed. I need to now differentiate and evaluate at the point when x is 0 minus sec squared of x. This is going to be a chain rule deal because a polynomial minus something squared becomes minus 2 lots of that polynomial, sec x. But then I have to times what sec differentiates to, and with practice you'll realise that's sec x times tan x. This is really easy to sort out because when I substitute in 0, this tan becomes a 0, so that wipes everything else out, so that's a nice fat 0. And now I've got f quadruple dashed x. 0 is when I differentiate and evaluate at 0 this horrible thing, which is going to be when I differentiate minus 2 lots of sec squared x times by tan of x. Okay, so what's that going to be? Well, minus 2 sec squared is just going to differentiate to this, but doubled, because minus sec squared differentiates to this. So because of the product rule, we're going to differentiate this, leave this alone. So tan of x times by the double of this, which is minus 4 sec squared x tan of x, plus, and now we're going to leave the minus 2 sec squared alone, so it's minus 2 sec squared x times by tan of x differentiated, which is sec squared of x. When I substitute in 0, I've got a 0 there, which times everything by 0 there, so this whole term wipes out. And then I'm going to have minus 2 lots of sec squared times sec squared, so that's 1 times 1, so I've got minus 2 times 1, so I've got minus 2 popping out here. Okay, so let's highlight them to make them super duper clear. Okay, express ln cosine of x as a series in ascending powers of x up to and including the term x to the 4. Okay, well, we've just dealt with all the derivatives evaluated at 0, so this looks like a Maclaurin series. So ln cosine x, so this is for my part C, ln of cosine x equals f of 0. Well, when I sub 0 into here, cosine of 0 is 1, ln of 1 is 0, so the first term just stays as a fat 0, plus f dashed of 0, which is a 0, so I don't have to worry about that, so it's plus a 0, plus, well, technically it was f dashed, where was it? It was this thing. So let's write that out to remind ourselves. The Maclaurin series is the sum of f of the ith power derivative at 0, x to the I over I factorial, where I goes from 0 to infinity. So for the third term, which is when I is 2, I've got the second derivative, which is minus 1, lots of x squared all over 2 factorial. For the third one, I've got f triple dashed, which is 0, so that just becomes a fat 0 times by the stuff, that's a 0. And then for the fourth one, the fifth term, but for the power fourth derivative, which should have been a quadruple dash, then I've got minus 2 lots of x to the 4 all over 4 factorial. So that means ln of cosine x is approximately equal to, the zeros go, minus 1 over x squared. Okay, so it's minus x squared over 2 factorial. And then 4 factorial is 4 times 3 times 2 times 1, and the 2 on here will cancel with that 2, so it's 4 times 3, so that becomes minus x to the 4 over 12. Yeah. So, yeah, we're going to get ln of cosine x, apparently to the first power of 4s, it's just going to be minus x squared over 2, minus x to the power of 4 all over 12. Then part D, show that using the first two terms in the Maclaurin series for ln of cos x, which we've got, the first two terms, with x equals pi over 4, gives a value of ln 2 of pi squared of that thing. Okay. Right, so first of all, when I've got x equals pi over 4, what is cosine of pi over 4? Cosine of pi over 4 is cosine of 45 degrees to root 2 over 2. So ln root 2 over 2 is 1 over root 2. Right. Okay, so that is the same as how many ln 2's? Well, there's a negative there. Well, how do I turn 1 over root 2 into 2? Well, I square both sides and then I reciprocate it. So there must be a minus 2 there. Right, so what it's saying is to find out ln 2, I substitute pi over 4 into here and then I times everything by negative 2. Jeez. Okay. So how about I times by minus 2 first of all. So ln of root 2 is going to be times everything by minus 2 becomes an x squared plus an x to the 4 over 6. And now I sub pi over 4 into there. So I'm going to get pi over 4 squared, which is pi squared over 16. And then, actually, I can tidy this up first, because x squared plus x to the 4 over 6 is the same as x squared times by 1 plus x squared over 6. So this is going to be pi squared over 16 times by 1 plus x squared, which is pi squared over 16. And then I can divide by 6 furthermore. So 16 times 6, get 96. So pi squared over 96. So was I supposed to get pi squared over 16 times by 1 plus pi squared over 96? Yes, I was. Tick boom. Yeah, quite tricky. But yeah, I mean, it's just a series thing. You sub it in. Once you have like this thing memorized, or at least you know where it comes from, I'll do more videos on it later, but it's really nice to play around with how sine differentiates to cos and so on and so on. You know, this video has dragged on for an hour and a half already. I'll do a couple more examples just to bang it in, but you know, maths is not a spectator sport. You need to do some maths on your own. I mean, I'm happy to go through some more examples. Anyway, right. Given that y equals x times e to the x. Interesting. To do the inverse of x e to the x is the lambda. It's the lambda function. No, what is it? It's the because it's a power tower. It's a is it the William Lambert function? Oh, I'm gonna have to Google it now. I know it's a thing. That's it. It's the Lambert W function. Anyway, you can Google that if you want to. It's brilliant. It's a good bit of maths. Okay, doesn't particularly matter here. So given that y equals x times e to the x, show that the nth derivative of that is n plus x e to the x. Okay, so probably going to have to use some proof by induction here. I'll gloss over it, so I will cover it at some point, but it's not particularly difficult. So if y equals x e to the x, let's differentiate it once. So just by the product rule, x stays as its own, and e to the x differentiates to e to the x, plus differentiate the x becomes a 1, times by, and leave the e to the x alone, you're left with that. And to tidy this up and factorise it, you've got x plus 1 times e to the x, which coincidentally matches when n is 1. You can treat this as a base case. Now, with proof by induction, what we do is we assume the rule's true, and we prove it for some next rule, for some next case. And if we can show that a domino effect is happening, and we can show that an initial case is true, then we just apply that domino effect on from the first case, and it goes on forever. So for n belonging to the set of integers, positive integers, which is what we're dealing with the differentiation, let's assume that dn by dy of dxn equals n plus x to the ex is true, and let's change a variable just to show that it doesn't matter where we start. Then let's try and find the next case, which is when we differentiate once more. So we're going to differentiate d to the ky over dx to the k, which means we need to differentiate k plus x times by e to the x. And then that's quite easy, because then we leave this alone, k plus x, differentiate e to the x by the product rule, plus differentiate k plus x is just 1, and then leave the e to the x alone. And when we combine these two, we're going to get k plus 1, lots of x, lots of e to the x. And when we differentiate dky by dx to the k, this is just d to the k plus 1, lots of y, over dx k plus 1. And this is clearly true. This agrees when n is k plus 1, and so we've closed that mathematical loop. To be honest, it's not that big of a deal. I will be going over proof at another point in time, but it's not important. There's so many different kinds of proof. We don't even cover anywhere near as much at A level, to be quite honest. We do proof by counterexample, or disproof by counterexample. We do algebraic proof, even though that's so vague and there's so many different ways you can prove things algebraically. We don't do any kinds of convergence tests, what I'm going to be talking about soon. Any ratio tests of convergence, that kind of thing. Yeah, there's just so many things. But anyway, so find the Taylor series expansion for x e to the x in ascending powers of x plus 1 up to including that term. Okay, so if it's around, so hold on. So if it's in terms of x plus 1, then for what values of x is this sequence around, or this series around? And the clue to that is it's got to be x minus a, which in this case is minus 1. So we're actually evaluating this around minus 1. If you always want to know where the series is being evaluated around, then just take the polynomial bit, which in this case is x plus 1, set it equals to 0 and solve for x. So really, we need up to the fourth term, do we? So, or rather to the x to the 4 term. So let's just crack out some derivatives. F of minus 1, f dashed of minus 1, f double dashed of minus 1, f triple dashed of minus 1, and f quadruple dashed of minus 1. Can probably bang these out fairly quickly, actually. So, what's the original thing? When x is minus 1, I've got minus 1 times by e to the minus 1, which is going to be minus 1 over e, not 0, and e. And then when you've got minus 1 in there, you can have x. First derivative is going to be 1 minus 1, which is 0. times by e to the minus 1, so that's going to be a 0. And then when x is minus 1 and n is 2, because it's the second derivative, 2 minus 1 is 1. So that'll be positive 1 e to the minus 1, so that'll be 1 over e. And then when n is 3, you've got 3 minus 1, because that's what x is, so that's 2 e to the minus 1, so that's 2 over e. And then the final one is going to be 3 over e, I'm pretty sure. Okay, so remind ourselves again, for the Taylor series, it's f of x is going to be from I 0 to infinity of f to the power of I evaluated at a times by x minus a to the I all over I factorial. So for the first term, that's when it's 0, I've got f of 0 differentiations, which is just the thing, which is here. So that's going to be minus 1 over e times by x minus a to the 0, which is a 1 over 0 factorial. So that's just going to be minus 1 over e. That's the first term. The next term would be f dashed when you sub in minus 1. Because that's a 0, I'm going to ignore it. So that term's done, that term's done. Next term, so plus, it's going to be f double dashed when you're subbing minus 1 over 2 factorial. So that's 1 over 2e. And then times by the x plus 1. And this, because it's the double dash, that's squared. So that term's done. For the third one, I've got f triple dashed when I sub in minus 1 is 2 over e. But then I've got to divide by 3 factorial. And then this is going to be x plus 1 to the 3. And then for the last one, I've got 3 over e, and then I've got a 4 factorial there. And then I'm going to have x plus 1 to the power 4. Okay. Right, first of all, it looks like these all have to the power, I could take a factor of minus 1 over e out, so it becomes 1 minus, and then the next term is going to be x plus 1 squared over 2. The next term, 2 over 3 factorial is just a third, because 3 factorial is 3 times 2 times 1, so the 2 and that 2 will cancel. So that's just going to be minus x plus 1 cubed over 3. So taking the e out. And the next term's a minus. And 3 over 4 factorial, I believe, is just going to be 1/8. Because 4 factorial is 4 times 3 times 2 times 1. And the 3 will cancel with that 3. So I'm left with 4 times 2 times 1 on the bottom. So that's just going to be x plus 1 to the power 4 all over 8. Other terms, but yeah, I think that's all they wanted you to do. So find the Taylor series expansion for x e to the x and ascending powers of x plus 1 up to and including the term x plus 1 to the 4, which I've done, and this is a good approximation using the Taylor series of x e to the x. So that'll be my final answer for D. I don't think I've made any numerical mistakes. Nope, cool. Right, last one. Sorry about that. Well, hopefully this should be just under the 2-hour mark. If you want to pause the video, give this a go yourself. Be my guest. Okay, so we've got dy by dx equals x minus y squared. So I think what this is getting at is how we're going to use Taylor series or Maclaurin series, it might be, I'm guessing, because we've got an x equals 0 going on here. We might have to use a Maclaurin series to essentially solve a differential equation. It's not a particularly easy one by the looks of it. So for AI, show that the fifth derivative of y with respect to x is that horrible thing. Jesus. Okay, so, okay, fine. Let's just do it. So if I've got dy by dx, right, okay. Let's define a few things to save a lot of time. Let's say d to the n y by dx to the n. I'm going to define that as dn, like that. So whenever I write dn, actually no, that's pretty bad. Let's have d subscript n. So if I say something like d2 3 like that, then I'm saying the second derivative cubed. So that's the same as the second derivative of x with y with respect to x cubed. Okay, so it's just a subscript, just to speed things up. So what have I got? I've got d1 equals x minus y squared. If I differentiate both sides, d1 just becomes d2 because I've differentiated it. X differentiates to 1, and by the chain rule, minus y squared with respect to x becomes minus 2y times by d1. Okay, think about it. If I've got a function of y, let's call it g, and y is a function of x, then dg dy, which in this case is minus 2y, and I have to times it by dy by dx. Okay, it's called implicit differentiation. We've covered that before in differentiation stuff, but essentially it's just a consequence of the chain rule. Okay, now I want to go all the way up to the fifth derivative, so you can see why I wanted to speed things up a little bit. So differentiate another time. So d2 becomes d3 when I differentiate it. 1 disappears, and now I've got a product here. So differentiate the 2y becomes minus 2 times d1 times by, and then leave the d1 alone, plus, and then differentiate the d1, which is going to become a d2, but then leave the minus 2y alone, so it becomes minus 2y. So let's get rid of this positive. Okay, that's d3. Let's move on. Differentiate a fourth time. This becomes d4. And now I've got this thing. Now to tidy this up, I've got d1 times d1. So let's just call that d1 squared. Let's differentiate this. So minus 2 lots of d1 squared. Well, by the chain rule, if this was minus 2x squared, it would become minus 4 of the thing to itself. So that's d1. And then I have to times it by the argument, which is d1 differentiated, which is d2. And now I can move on, and I've got minus 2y d2 here. So I'll leave the minus 2y alone, 2y, differentiate the d2 to make it a d3, and then plus, differentiate the 2y, becomes a minus 2 times d1, and then leave the d2 alone. Now that's clearly going to be a minus. Let's put a thing around the d3, that's around the d2, that's around the d1. The d4, let's tidy that up a little bit before we go on. I've got a d1, d2 there, and I've got a d1, d2 there, so let's tidy that up. So I've got minus 6 lots of d1 times by d2, and I've got minus 2y lots of d3. Okay, so that's my final answer for d4. Now I just have to differentiate one more time, so d5 is going to be I've got minus 6 lots of the product of d1, d2, and I differentiate. So differentiate d1 becomes d2, leave the d2 alone, so that's squared, plus leave the d1 alone, now differentiate the d2 becomes a d3. And now minus 2y d3, so I've actually got minus, and then 2y differentiates to 2 d1, leave the d3 alone, plus leave the 2y alone, and then d3 differentiates to d4. Okay, so I think actually I'm more or less ready to go. So I've got d5 here. I've got a minus 6 d2 squared. So I've got minus 6 d2y by dx squared squared. I've got a minus 6 d1 d3 there, but I've also got a minus 2 d1 d3 there. So I've actually got minus 8 lots of dy dx times by d3 dy by dx cubed. So that term's done, that term's done, that term's done. And now I just have a minus 2y lots of d4y by dx to the 4. Now I'm done. Actually saved a lot of time by doing that. So what have we got? Right, so we've got to the power of 4s. Yep, so ay is minus 2y, so we've immediately got that a is negative 2. B is the amount of dy's by d3's, which is here, so I've got b is minus 8, and then I've got c's, lots of the second derivative squared, which is over here, so clearly c is just minus 6. Wasn't too bad. Okay, hence find a series solution in ascending powers of x as far as the term x to the 5 of the differential equation I, given that y equals 1, x equals 0. Right. Oh, plum dums. Right, okay. So another way of writing it is that d0, which is just y, equals 1 when x equals 0. So really, I need to know what all these derivatives are when x is 0 is y is 1. So let's do that. So when x is 0, y is 1, d1 is 0 minus 1 squared, so that's minus 1. Okay, second derivative. That is 1 minus 2 lots of y. So that's 1 minus 2 lots of 1, because y is 1, times by d1, which is minus 1. That looks like it's going to be 3. Now it's really important you don't mess this stuff up, because stuff carrying forward is going to make this a nightmare. d1 is definitely minus 1. Minus 2 times 1 times minus 1 is plus 2. So this whole thing becomes plus 2. 1 plus 2 is 3. Right, fine. Moving on. Third derivative is minus 2 lots of d1 squared. So minus 2 lots of d1, which is minus 1 squared, minus 2 lots of y, which is 1, times by d2, which is 3. Okay, you know what? This is going to get confusing. So let's put y, d1, d2, d3, d4, d5 up here. Y was 1, d1 was minus 1, d2 was 3. No, wait, yes, d3 I'm still working out. So minus 1 squared is 1, so that can go. Minus 2 times 1 times 3 is minus 6. Minus 2 minus 6 is minus 8, so that number needs to be a minus 8. Next up, I've got minus 6 lots of d1, which is minus 1, times by d2, which is 3, minus 2 lots of y, which is 1, times by d3, which is minus 8. So minus 6 times minus 1 times 3 is 18, minus 2 times 1 times 8 is 16, positive, so 18 plus 16, that makes that 34. And then for the final one, I've got minus 6 lots of the second derivative, which is 3 squared. Yep, minus 8 lots of the first derivative, which is minus 1, times by the third derivative, which is minus 8, minus 2 lots of y, which was 1, times by the fourth derivative, which is 34. Oh boy, right, okay. Minus 6 times 3 squared. Well, 3 squared is 9, times minus 6 is minus 54. Minus times minus is a negative. 8 times 1 times 8 is 64. Minus 2 times 1 times 34 is minus 68. So minus 54 minus 64 minus 68 is negative 186. So because this is centered around x equals 0, we're going to be using the Maclaurin series here. I want to go up to x equals 5. So that shouldn't be too problematic. So that means the solution is going to be y, which is f of x, by the way, is approximately equal to, when I sub the value in, x is 0, which is 1, plus f dashed of x, which is minus 1, times by x, that's minus x, and then f double dashed at that point, which is 3, over 2 factorial, which is 2, times by x squared, plus f triple dashed at that point, which is minus 8, over 3 factorial, times by x cubed, plus f quadruple dashed, which is 34 over 4 factorial, times by x to the 4, plus f quintuple dashed, which is minus 186 over 5 factorial, x to the 5. Okay, let's tidy some stuff up. So a polynomial that best approximates this as a solution would be 1 minus x plus 3 over 2 x squared minus, And 8 over 3 factorial, I believe, is 4/3, because the 3 factorial is 3 times 2 times 1, and the 8 and the 2 will cancel like so. 34, 4 times 3 times 2 times 1. The 34 and the 2 will cancel to get 17. So I believe that's going to be 17 over 12 x to the 4. And 186 over 5 factorial. Well, 186 divided by 2 is 93. And then 93 divided by 3 is 31. So it's going to be 31 over 20. So I'll make that 31 over 20 x to the 5. So in the neighbourhood of the point 0, 1, the curve y is 1 minus x plus 3/2 x squared minus 4/3 x cubed plus 17/12 x to the 4 minus 31 over 20 x to the 5 is a good approximation of what's going on in this question. And actually, it's an incredibly powerful tool to solve, especially if I'm interested in say working out what y is when x equals say 0.2, then I could have substituted 0.2 in there. It's fairly close. It would have been a good approximation, and so on. So yeah, interesting. I hope you enjoyed that. Yeah, that'll do for now. Toodaloo.